Hi everybody, welcome to another IZ8 DWF arcade repair video. As you can guess, this is a monitor, however it is a quite rare one, a color vector monitor made in Italy by Hantarex. This monitor does not even have a model number and I couldn't find any documentation about it. I know another Italian arcade enthusiast that owns an Hantarex color vector monitor, but as far as I could understand it is a different revision than this one. In this cage there is the anode high voltage power supply, by the way. Together with the monitor I have received the complete board set of a Space Fury clone made in Italy by Rumiano and called Advisor. And the complete power supply too. Some time ago I published a video about the reverse engineering and fix of this very same power supply. A link to it is down below in the description. And, by the way, this is the original cabinet of this game. It is a nice one indeed. Both the power supply and the board set should be in good working conditions, so now we'll try to bring this monitor back to life. However, this monitor has already seen quite some rework before getting here. Luckily, these labels list all parts that have been already substituted. Of course, before trying to apply power, I'm going to completely disassemble it, carefully inspecting every board and testing all components that can be tested at power off. After removing the top cover from the final transistors cage, we can already see 4 transistors. These are for one axis only. It is probably a push-pull configuration with each leg having 2 parallel units. To remove this assembly from the chassis, a few connectors need to be unplugged. And this little one is for the big AC fan. Of course, I'm marking the connectors so I don't risk plugging things in the wrong places when reassembling. This monitor is completely undocumented until now. After removing the cage, I can already see a resistor moving too freely. Now I need to separate the 2 heatsinks by removing these nuts, and then slide out one of them. Even this solder joint is completely open. So I started soldering back the power resistors, putting heat shrink insulators on their legs. I've also temporarily removed the base connection from the transistors in order to test them separately with the multimeter. Nothing suspicious was found at this stage. The next easy one is the neck PCB. Solder joints here look quite bad. Notice that some of them are visibly cracked, so I'm going to just reflow the whole PCB and test all semiconductor junctions as always. On the yoke we have an unsoldered wire. So that was soldered back where it belongs. They have just used 2 parallel wires to share the currents going to the deflection coils. To remove the deflection board, I need to unplug and mark a few more connectors. This is the largest PCB on this monitor. It comprises a dual AC to DC power supply with no regulation and XY deflection circuitry. First of all, I've noticed one transistor moving on its heatsink. But that's just because the nut is missing, not a big problem. Then, as usual, I've started probing all semiconductors junctions. And this one looks definitely suspicious. The voltage drop is too low. And it's also the same in both directions. So I've unsoldered the suspicious transistor. But it looks fine out of the circuit. Since on the other deflection circuit the transistor in the same position doesn't show any low reading, I've started checking if the two circuits have differences. Notice that these three resistors were replaced because some or all of them were burned. In fact, there is a burn mark on the PCB. The corresponding resistors on the other axis are R34, R35 and R36, so the same order was used originally to replace the burnt ones. Unfortunately, by circuit inspection I could see that the designers didn't bother to have consistent component numbers between the two deflection circuits, and so the correct place for the 100 ohms and the 330 ohms resistors is inverted between the two axes. Since I have to swap them, I will also try to remove as much carbon residues as possible from the PCB. So the two resistor was swapped and I verified that the transistor junction now can be checked in circuit like it's twin one. By removing one single screw, we can extract the high voltage power supply from the chassis. And then two more screws hold the PCB to the cage. The PCB can be finally extracted from the metallic cage. Even in this case, the inspection showed a bolt that needed tightening and some suspicious solder joints, but no failed components so far. As I mentioned, this monitor is powered directly with a center-tapped AC transformer. This is the connector coming from the secondary windings of the transformer. Now, since the big smoothing capacitors on the deflection PCB have a voltage rating of 80 volts DC, I have calculated the maximum AC RMS voltage that will not exceed the capacitor's rating. I expect the actual voltage from the transformer to have at the very least 10 volts safety margin from the maximum. So let's measure one tap. Well, almost 47 volts, right at the limit I expected. On the other tap shows obviously the same voltage. So let's measure the transformer primary side. In this moment the mains voltage here is 227 volts, as low as it usually gets at night. On the unconnected primary tap I can measure 248 volts, so it's probably wise to use the high voltage primary tap. And now, of course, the full mains voltage is across the whole primary winding. And with the primary tap change, the AC output voltage now dropped to 43 volts on each secondary winding. This gives a better margin. Before powering on the monitor, I'm going to do some basic checks to the game board set. First of all, I verified that all power rails are present and in the correct range. Here I'm measuring the plus 5 volts rail. Next, I'm going to check with the oscilloscope if the signal outputs going to the monitor look healthy. The top connector with the red, green and blue wires has the color intensity signals, and the bottom one is for the X and Y deflection signals. I'm looking now at one deflection signal and it appears stuck to one voltage rail. But if I move the power input connector to the game board, it starts working momentarily. So I decided to apply some contact cleaner spray on all the power supply contacts. Now both deflection are working without issues, even if on the scope it's difficult to read anything, because it's not using any brightness information but only the X and Y signals. The play feed, however, looks good enough. For the initial power on attempts, I have connected a 100 watts incandescent bulb in series with the transformer's primary to limit the current and avoid anything to smoke or explode in the monitor. I've also placed the high voltage probe in contact with the anode connection, so I can see if the high voltage power supply works. So let's power on. Well, the bulb glows at maximum brightness forever, and the multimeter doesn't seem to detect any high voltage. I think the 100 watts bulb is way too small for a 19 inches color vector monitor, so in order to reduce the load, I measured the Gauss coil resistance. As you can see, it's less than 27 ohms. Now, at power on, this resistance would alone draw 273 watts until the PTC increases its resistance enough to cut this load. So from now on, I leave the Gauss coil unconnected. Well, that didn't make any difference apparently. I have now connected to the power transformer only the AC fan connector, so I can check if the fan alone is at least starting fine. And yes, I can hear the fan starting. And that's surely loud. Since I don't have incandescent lamps bigger than the 100 watts ones, I need to use at least two of them in parallel to protect this monitor even with the Gauss coil and the fan disconnected. So let's see what happens. Well, now the meter shows a few kilovolts and I seem to hear some high voltage hissing. I've connected a third 100 watts lamp in parallel now. Now the meter shows more than 10 kilovolts and the hissing sound is clearly audible, but I can also see a trail of smoke from the deflection board. Clearly I cannot troubleshoot the faults with the series lamps and things hissing and smoking, so I've decided to reverse engineer the deflection board schematic first. I've initially drawn the vertical channel, since the smoke appeared to be coming from that half of the board. I expect the two channels to be identical except maybe a few resistors values. This deflection circuit is a bit complicated compared to other color vector monitors. However, let's quickly see how it works. The input signal goes to one base of a PNP differential pair. The other base of the pair gets the deflection current sense signal, of course. The emitters of the differential pair are fed with a current source circuit. The current source bias voltage is obtained with two series diodes in order to compensate the two base temperature drifts of the current source itself and the differential pair. The inverting output of the differential pair goes to a common emitter NPN stage and then to a push-pull emitter follower made with two complementary Darlington pairs. TR5 is the common emitter amplifier. Notice all those diodes and the capacitor C4 that together implement a so-called Baker clamp to avoid the transistor to enter the saturation zone and becoming too slow. The collector output of TR5 goes then to the Darlington pairs. The pull pair is shown here. The output of the Darlington driver goes to the final deflection transistors housed in the external heatsink. And here is the last part of the Y deflection circuit. This is the base bias generator for the Darlington drivers. We have another current source obtained with three series diodes biasing a transistor and then another transistor working as variable clamp that can subtract part of the current from the base drive bias. And of course we have the other half of the push-pull Darlington shown here. A good side effect of reverse engineering is the close observation of almost all components, so I've spotted this Zener diode that seemed in a really odd position. This was D12, part of the differential pair current source circuit. It's one of the components that was substituted before the monitor arrived here. In this case, a Zener diode wouldn't cause much troubles, since these diodes are always forward biased, but I've substituted it with a 1N4148, since it's the appropriate part for this job anyway. I've also decided to check the ESR of a few tantalum capacitors that are part of the spot killer circuit. And all of them show very high ESR. Since their capacitance value was low enough, I decided to substitute all of them with small film capacitors. These will never degrade in the future. Now that I have a schematic, I can power the deflection board with plus and minus 15 volts from a current limited bench supply and start looking around for possible faults. By the way, I can use low voltage rails because the board doesn't have any voltage regulator. I can compare readings between the two channels. And here I see the first problem. This transistor shows an emitter to base voltage difference of almost 10 volts, and that's not normally possible. Here is the suspect transistor. Base to emitter junction looks good, and base to collector too. But collector to emitter is shorted. This is a very peculiar failure, and I seldom test this combination during the first inspections, unfortunately. This other transistor of the pair looks good anyway. Now, with the transistor replaced, let's look at the deflection outputs. This is the X-yoke output and there is no voltage across it, which is what I expect with no input signal and no current flowing. But on the Y output there are a few hundreds millivolts, which is suspicious. Comparing the voltage readings on the transistors between the two channels, it seemed that the biggest differences are on the NPN Darlington pair, so I've removed both of them to be checked out of circuit. Indeed, one of them shows a very low current gain. 17 is too low for almost any small transistor. In fact, the other one shows a current gain of 58, which is an acceptable value. The datasheet shows a minimum gain of 25, by the way, so the one showing a gain of 17 is surely degraded. Now, the original transistor is an MPS U10, and this has a very uncommon pinout, with the center pin being the base connection, and the tab instead being the collector. I don't have any of them as pairs, and I also decided not to trust the few sources I've seen online for this old transistor, so I'm going to replace it with a modern high voltage transistor that has a different pinout. Base and collector pins have been twisted and insulated. The replacement will go on the lower current side of the Darlington pair anyway. So after the substitution, I'm going to check if any current flows into the yoke. Of course, using the multimeter in current mode in place of the yoke. We have less than half a milliampere, which is okay. And a slightly lower current on the X yoke. So it's time to get back on the real monitor. Now the lamps get dim, that's good. And with no inputs, the voltage on the Y yoke is very low. And of course we can still hear the high voltage noise, but that's another issue. Now I've connected the video output from the game. And wow, something actually appears. Looks like the red signal is missing anyway. But good progress so far. This is the test screen of this game, and indeed the red color seems missing. Well, actually it was only the video output connector that needed a good cleaning. However, the vertical sides can't be stretched more than this, so there is still more work to do. After the fix, the sound disappeared and I can set the anode supply voltage. Since I don't have better information, I would set it to 19.5 kV, like I've seen in the manuals of the majority of the other color vector monitors. And in case you're wondering what the fix was, I first ran the monitor with the high power supply open and in complete darkness. Usually the source of high voltage hissing is also making a visible spark or corona, and indeed I could see a faint blue glow around the high voltage cable connection on the transformer, but that didn't show in the camera footage. After powering off and discharging the high voltage from the anode cap, I've noticed that this locking nut couldn't be tightened enough to completely block the cable that could still move back and forth inside the transformer. So the fix consisted in removing the cable to cut the burned end and expose a clean copper segment, reinsert the cable inside the transformer and add some hot glue to hold it firmly in place. The camera battery in this case decided to die soon after I started filming the whole procedure. As we have seen before, the test screen looks too much squeezed vertically. The Y-side trimmer couldn't stretch the deflection more than this, but on the X-axis it had no apparent problem. And it's not only a test screen issue, as even the game field appears to be too narrow, with the score position too far away from the top. I had already suspected that something was wrong during the reverse engineering, since the current sense resistor values measured differently between the two deflection channels. The x-axis resistor measured 3.3 ohms and the y-axis one measured 6.3 ohms. Of course, on this schematic there is the correct value because this is the latest revision. Now, both resistors are rated for 17 watt power dissipation, and if we assume a peak deflection current of 2 amperes based on the 4 amperes fuse rating, then already a 3.3 ohms resistor would peak at 13.2 watts of power dissipation, and the resistor on the vertical channel would peak at 25.2 watts of power dissipation, so clearly that made me suspect the original value should be much lower than 6 ohms. A drifting current sense resistor can explain why the deflection amplitude is too narrow. Of course, I have checked all the other color vector monitor schematics I could find. This one is part of the Wells-Gardner 6401 that has a parallel push-pull deflection driver configuration for the final transistors like this Hantarex one. Notice, however, that the collector supply on the final transistors are lower, more or less plus and minus 48 volts, and both are regulated values. On our Italian monitor, both supplies are unregulated and reach more than plus and minus 50 volts. Let's also observe that both yoke fuses on the Wells-Gardner monitor are rated at 3 amperes, unlike the ones I found on the Hantarex that are rated at 4 amperes. I believe, however, the actual deflection currents are similar, since both monitors have the anode high voltage set at 19.5 kV, and probably they have a very similar yoke windings. Even the supply rails going to the first amplifier stages are lower, by the way, because using higher voltage makes no improvement on the monitor specifications. It just adds power dissipation and the need for components rated for higher voltages. And last, notice that yoke current sense resistors have 1.5 ohms value for both axes, and they are rated for only 10 watts, not 17 watts as on the Hantarex monitor. To me, it seems that Hantarex designers kind of needed to dissipate more power to help maybe the final transistors remaining in their safe operating area, and that is because they used two high voltage rails with no DC regulation. So I've decided to remove both resistors. This one was on the vertical deflection circuit, and this one was on the horizontal circuit. Luckily, one of them has still some readable marks. I could already tell the original value from close inspection. But to be 100% sure, let's take a small portion of the previous picture and then run some color filters with GIMP. The 2R7 characters are clearly visible, so I've confirmed that both resistors drifted over time, probably due to the very high power dissipation. It would be quite easy to modify the current feedback circuit to use lower value resistors, but as I said, I'm afraid this very high power wasted on them is needed to help the final transistor to survive, so I've ordered two resistors of the original 2.7 ohms value. Of course, the replacement resistors have the same dimensions and fit perfectly in the original mounting supports. And after the replacement, the deflection sides could be finally set correctly. So far, so good. At this point, I tried running the monitor without the series lamps, and it actually ran without issues the first time. But as soon as I power cycled it, both fuses on the power input blew instantly. So I've reconnected the lamps and started looking around at the deflection waveforms. This is the vertical yoke drive and it shows a problem. The problem is this DC offset. In the intervals with no deflection, this voltage should be exactly 0. The horizontal yoke drive also shows a DC offset voltage, but much smaller. And just for confirmation, this is the drive signal from the game board set and there is no offset in it. So clearly there are still faults that I need to find, and it's time to go back to the bench with the low voltage supply. Out of desperation, I pulled the NPN transistors of the horizontal Darlington stage. As we have seen, one of them in the vertical channel had a degraded current gain, and even here one of them indeed showed a gain of 39, which is just right at the low end according to its datasheet. The second one, just like happened for the vertical channel, shows a more reasonable current gain. So also in this case I've substituted the tired transistor with a more modern one that however requires a twist of the base and collector legs. Of course I knew that this wasn't going to fix the DC offset problem. This time I'm jumpering with the yellow wire the yoke terminals so the current feedback circuit is complete. Anyway, in a feedback loop, it's not easy to understand where an erroneous signal is generated. But after all, it really seems that the first differential pair is never balanced. So this is one of the differential pair transistors. I've soldered a few kiloohms resistor to the emitter leg and that in turn is connected to the positive supply. The base is open and I'm going to see if any current flows from emitter to collector. And wow, that's almost 1 milliampere of leakage at 15 volts on a transistor rated for 65 volts. So I've desoldered all the remaining transistors from the differential pairs of both channels. Here's how a healthy transistor should look on the curve tracer. In particular, the line at the top of the screen should be straight over the first graticular line, as this will be the collector current without any base drive. However, all the BC556 transistors part of the two differential pairs showed a very high leakage, like this one with these evident overshoots. Even this one shows a similar behavior. And this other one looks like having a resistor in parallel between emitter and collector, as all the curves have this funny slope. And as we have seen before, one of the transistors of the differential input pair on the vertical channel was substituted due to a near short circuit between emitter and collector. So that means that all four BC556A on both channels were faulty. But what's even more interesting is that both the BC556A used as current sources didn't show any sign of leakage. Unfortunately, I had already ordered some BC556 replacement transistor before realizing this fault cannot be caused by an unlucky batch of transistors. As we have seen, the transistors used are BC556. The limiting value for the emitter to collector voltage for them is 65 volts. At the beginning, we have seen that the power transformer has an IC output of 43 volts, and that after switching the primary tap to 240 volts. This means that each DC rail will have an absolute value of nearly 60 volts, and the DC voltages will be also dependent on the actual main voltage, since there is no regulation. Now, in a circuit like this differential amplifier, with both supply rails close to plus and minus 60 volts, it's easy for the transistors to momentarily see an emitter to collector voltage that exceeds the 65 volts limits, for example during the fastest deflection changes. In fact, the high emitter to collector leakage, or in the worst cases, the emitter to collector short circuit, is a typical failure mode when the maximum collector to emitter voltage is exceeded even for many short intervals during the life of a transistor. So, in order to allow this monitor to have a longer life, we must substitute the BC556 with different transistors, rated to, at the very least, 80 volts. Now, the problem is that most high-voltage transistors don't have a pinout similar to the European BC556. The closest one I could find are the MPSA ones that have the base pin in the middle and can be inserted, rotated by 180 degrees with respect to the original ones. The MPSA 56 would be a good candidate, but I couldn't find 4 of them in my spare parts. I could instead find 4 MPSA 92 transistors that are rated at 300 volts maximum, which is really overkill, but I didn't want to wait again for more spare parts to fix this monitor. And finally, no more DC offset on the deflection drive waveforms. This is the measured DC rail voltage without the series lamp, and it's less than the calculated value because of the transformer losses under load. However, it is still too high for reliable operation with the old transistors. Now the monitor works fine without the series lamps. It can even be power cycled without issues. However, to play a game I had also to substitute some switches that weren't working anymore. So it's all for this video. I hope it was interesting and that you learned something. If you have any question, use the comment section below. Have a nice time and thank you for watching.